All right, welcome to the quiz review. I made up this document real quick out of the problems in the end of chapter practice. So hopefully this helps you out. And let's walk through it. So the first one is from 4.1. So this is the straightforward simple interest one where we have P equals, not P equals, sorry. Y equals A times B to the power of X, where B is our growth factor. So that's 1 plus R for growth, or 1 minus R for decay. So let's look at this problem. Write and solve an equation to determine the balance after 25 years in an account that had an initial investment of $18,000 at 3% interest compounded annually. So we're increasing. That's our initial value, and this is our time. So when we look at this, we don't know our Y, but our A, we often call P as well, which is our initial value. So that would be the $18,000. Next, we need to find our B. We have this rate as 3%, but we can't just add 3% to 1. So we're going to actually use the decimal. So we get 1.03 as our base, our B. Next, we have to figure out our exponent. Here, we're lucky enough that we actually have a variable right away, but this problem wants us to write the equation. So we would put in X for now, and then after 25 years, that means we need to put in the exponent of 25. So we need to plug this into our calculator. I'm feeling lazy, so I'm just going to use Desmos. So that was 18,000 times 1.03 raised to the power of 25. So that's 37,688 and 0 cents. So I had two parts right there, the equation and the final answer. Moving on, now we want to find the interest rate. When the amount of 15,000 grows to 15,525 in the first year and in the second year. So remember, we said we don't need all this information. So we can either go from initial to first or from initial to second. And I'll show you both ways here, but you really only need to do one. All right. So if we go from initial to first, what we're saying is we're going from 0 in year 0, we have $15,000. And after 1 year, it grows to $15,525,000. So we could use our equation or not. This one's a little bit straightforward, so we don't have to use our equation. We could do our new divided by our old. All right, and then if we do that in our calculator, we do that in our calculator. We get 1.035. But remember, this is B, which is 1 plus R. So we have to subtract 1 from this. So we get this is equal to R, but we're probably more used to writing that as a decimal, which means we have to move it over 2 places, so 3.5%. All right, that's an easy, fast way, but that's when we have year 0. and year one. It's a little bit more complicated if I don't give you year one. Like in this example, we still have our initial value of $15,000, but what if we don't have 1 year away? What if we have a more complicated number? So let's see what we have to do. Here we do have to actually use our equation. So we have y is equal to p times 1 plus r to the power of x. So if we look at this, this is x, this is y, this is p. So we have $16,068.38 equals $15,000. And then 1 plus our rate raised to the power of 2. We would divide this out. Okay, so we get 1.071. All right, but now we have to deal with the square. And the only way to undo a square is a square root. And now they cancel out. That means on this side, we have to take the square root of that number. So we can do that quickly in Desmos by just adding. Thought we could. Okay, so square root 1.071. So here we get, if we round to the same decimals, 1 plus r is equal to 1.035. So r is equal to 0.035, or r is equal to 3.5%. So we still get the same answer, just a little bit different of work. So let's keep moving on. Next problem. A company that makes mobile apps has products of $7,000 in the first year. The CEO says that this will triple each year over the next 5 years. First, we want to write an equation. Then we want to figure out after 5 years, how much money will we have. So let's see. First, we have to write our equation. We don't know how much money we have after a certain amount of time, but we do know how much money we start with, which is at $7,000. And then remember, we said B was our growth factor, which is how much we multiply by every year. Not our rate, but our growth factor. So if we look at this, we have all this information. The only one which is like a factor would be that triple, which means we increase by a factor of 3 every year. So this is part A, our equation. And then moving on to part B, we're trying to say, after 5 years, will we reach that mark of $1.5 million? So let's see. That means X is equal to 5 years. So we just have to plug it in. And we get 1,701,000. Which is greater than 1.5 million. So yes, the goal was met. All right. So that was 4.1. Now we're moving on to 4.2, which is when we're introduced to this one. Y is equal to the principal 1 plus r over n raised to the n of t. This is where we had n was the number of times compounded. All right, on that green worksheet, you had the number given to you, but on this, we have to think about what these words actually mean. So let's look for important information. we have determined the interest earned after 5 years in an account that had an initial investment of $25,000 at an interest rate of 3.5%, and it was compounded daily. So let's try to write this out. Nowhere in there says how much money we have at the end, so y stays our variable. P is our principal, so our initial value, and our story problem said $25,000. Next, we have to do 1 plus and our rate. Our rate should be in decimal, just like in the other problem. So we have to convert our percent, 3.5%, to our decimal. All right, and then now we have to figure out n. That's the number of times compounded. It says compounded daily. So for us, that means 365 days. And then we put n up here as well. But up here, we have to multiply by our t, which is the number of years. So here that means 5 years. It's going to be a huge number, right? We're going to plug this right into the calculator. For you, that means when you plug it into the graphing calculator at school, we can type it in just like this. But once we get to our exponents, we have to be careful. We should put it inside parentheses and actually use the multiplication key, not the parenthesis key, so we can get something like this. If we don't set it up like this, the calculator is not going to do it correctly. All right, so let's go to Desmos. We have $25,000. 1 plus 3.5% divided by daily, right? And that's raised to the power of parenthesis 365 times 5. All right, so it looks like it grew to 29,780. Sorry, lost where I was. $29,780.91. So our y is 29,780.91. The question asks for how much interest did we earn, which I won't ask you this question, but that means how much money did we make on top of the 25,000. So we have to subtract the $25,000. So our actual answer for how much money we made, not how much money we have after 5 years, but how much money we made, the bank gave us, would be just the change in our balance. All right, so let's move on. Determine the balance after 10 years in an account that had an initial investment of $25,000 at 3.5%, and it was compounded quarterly. So same setup, mostly from the one above, but now we have a different amount of compounding. All right, so far it looks exactly the same, but now because we have quarterly, that means 4 times a year. And now instead of 4 years, we do 10. All right. So let's just plug that into our calculator. I might just, whoa. Yep. I'll rewrite it. $25,000. 1 plus that 3.5% divided by 4 now because we did it quarterly, raised to the power of 4 times 10 years. So we get $35,000, 422.72. And that would be our final answer here. Next, we have to determine the amount of money that needs to be invested when we have 6% compounded monthly, where our final amount is $20,000 after 15 years. So this one's going to be weird because it's not exactly the same work that we've been doing. So remember, we had this equation. Now that we can't really see it, it's off the screen. All right. Determine the amount of money that needs to be invested. That means our P is our variable. We have everything else. So it's 6%, so 0.06 divided by, and then if it's compounded monthly, there's 12 months in a year. So 12 is n, so we plug that in the bottom of the fraction and in the exponent. We do this for 15 years, and we want to figure out what money do we have to start at if we need $20,000. So maybe this is like someone had a child and they want to raise $20,000 to buy them a car on their 15th birthday or something like that. So we have this set up. What we need to do is figure out what this part of the equation is equal to. So we're just going to plug only that part into the calculator. So we have 1 plus 6% divided by 12, because we're doing it monthly, raised to the power of 12 times 15 years. And see what I did? I forgot to put my parentheses around my exponent, and even Desmos got mad at me. So that's 2.45. So $20,000 equals P times 2.45. All right, so then we divide that over. So here we get $20,000 divided by 2.45. So it looks like we only need to put $8,163.27. So if we put that into the bank as soon as our child was born and we had 6% interest compounded monthly, by the time our child gets about driving age, we could buy them a nice $20,000 car, which who knows what that would actually buy us in 20 years. So that was the end of our examples for when we used this equation. The next section that we're going to talk about is 4.3, which is when we saw the word continuously. We got a new equation, which is y equals the principal times this new number, which we just call E. It's short for Euler's constant. We raise it to the power of RT. We don't need to know it, but E is approximately equal to 2.71. All right, so let's try to use it. Determine the balance after 20 years in an account that had an initial investment of $25,000 and an interest rate of 5%, and we compound continuously. So let's do this. Y is equal to, P is still our principal, so that's how much money we start with. And now we have E instead of this 1 plus R over N. A little bit more simple, right? Our rate is 5%, which we still need to change to a decimal. And our T, or our X, is our number of years, so we do that for 20. We can just plug that right into the calculator. All right, when we plug this into the calculator, what you guys are going to do is $25,000. And then to get this E button, you have to press second ln, and you'll get something that looks like E with this dotted box, which means we have to fill in that exponent, which is good for us because we actually want to fill in that exponent with our completed multiplication here. All right, so let's try that. $25,000, and I don't see E on Desmos, so I need to go into functions and see if it's there. So stats. Let's see if I just click E. There we go. Okay. So here we did E, but we need to raise it to the power of, and we had 5% times 20 years. So we get $67,957.05. All right, so let's see our last problem of this quiz review. The population of deer on an island is growing exponentially. The first year the population was measured and there was 50 deers. 5 years later, there's 552. All right. Write an exponential function that represents the number of deer on the island given the years since the initial population count. All right. So this is a natural phenomenon. These are deers. This isn't a bank where someone can sit down and decide when this growth is happening. So whenever there's nature, we're using E. Remember how we call ln, which is log base E? We call that the natural log, and this is kind of why we have this little naturalness to it. So we need to use our equation for this. P, for us, we use it a lot for principal, which is for money, but that's just our initial value. So that would be our 500 deers. All right. We have 552 at the end. We have E. We don't know our rate, but we do know that we have 5 years. All right. So we need to figure out what a rate is if we actually want to figure out our equation. So first we have to divide by 500. So we get 1.104 equals e to the power of 5 times r. Okay. This was supposed to be before we had logs, so we don't know how to solve this yet. So what we talked about in class is we can actually graph these two things. So y is equal to 1.104, and then y is also equal to our equation, which is e raised to the power of 5, and we have to say x here. So, right, we need to figure out where these cross. This will be very hard to do in your table, but it crosses at 0.02. So that means our r is equal to 0.02, and that we got by graphing. If we wanted to use logs, this would turn into the natural log, which is log base e, and then we have to figure out what goes next. E is already next to 5r. We don't want 5r to still be next to e, so we want to put this here. Okay, and that is equal to 5r. So we can now use our calculator again and do our ln of 1.104, which is about equal to this number, so that's 0.0989. Divided by 5. So we get r is equal to 0.0, and we have 1978, whatever, so that's basically just 2. So again, we get the same rate, which would be 2% no matter what. So when we actually write our answer for A, we get our 500 deers that are increasing at this percent every year continuously. Now we want to know how long would it take for the number of deer to double All right. So double 500 is 1,000. So we plug this in, divide by 500. So that's where that 2 comes from because we're doubling. And as again, we need to solve for a variable that's in the exponent. So now we have to graph some new equations. So here instead of this, we have 2. And here we have 0.02. So we need to figure out where they intersect. Ooh, it's taking a long time. All right, so it looks like we have 34.657. That was from graphing. But remember, we should always round up. So 35 years would be our actual answer. All right, we could do this by not graphing. We could use logs again. So we get natural log of 2 equals 0.02x and divide that 2% over on that side. So if we do this again, 2 divided by the natural log of 0.02. I messed that up, didn't I? The natural log of 2 divided by 0.02. All right, and we still get that same 35.657. So even with the log, we get x is equal to 35 if we round up years. So that was just a little example for what might be on the quiz tomorrow. You should be expecting to plug it in and just solve for our final value a lot more than you have to do the other stuff. And I want you to be able to set up some exponential functions like what we did in the story problem just now with the deer and in the one from the 4.1 problem. Good luck.